How is the conference so far? Yeah, good sessions? Great, let's keep it going. Good afternoon, everyone. Thank you for coming to my session. Thank you for spending this part of the afternoon with me, and of course with TensorFlow and natural language processing. My name is Barbara, and I keep getting those questions. If you're not Polish, you don't realize that Barbara and Basia, the same name, one is abbreviation of the other. I don't mind which one you're calling me. So those are not two different names. And because I have different handlers, depending how I felt that day, it may be a little confusing. So please follow me on Twitter, contact with me if you have any questions. Yeah, I'm happy to connect with you and answer them. So who am I to talk to you about TensorFlow and natural language processing? I am machine learning strategic cloud engineer. Actually, recently I started leading a team of machine learning strategic cloud engineers in Europe. So my job title is expanding, I would say, with every year, and has a lot of buzzwords in it. So what do we do as strategic cloud engineers at Google? We work in professional services, and my team is focusing on machine learning, but we have teams focusing on infrastructure, app development, security, data. And each team, each strategic cloud engineer, is working with consultant in a tandem to provide some different packages to our customers. So in terms of machine learning, for example, we provide packages like Cloud Discovery ML, so we help customers to discover their use cases in the machine learning space. We have something that we call MVM, which is short for Minimum Viable Model. When we build the model for the customer, machine learning model, that is solving specific use cases. We perform feasibility studies, cloud deploys when you want to productionize your models. So this is what we do. And majority of our work is to, of course, leverage the cloud for the customer, Google Cloud, but also to work with TensorFlow. This is the most popular technology that we work with customer day to day. My background, though, is in software development. So I used to be a .NET programmer. I switched the field into the data science. And machine learning is my favorite topic. That's why I've put my career on it at the moment. So you have all of the credentials. I own all the domains. They all lead to my blog. It's a huge word because I blog like twice a year. But still, you can easily connect through that blog with me, or just tweet me or send me the email. So let's get started. This is the plan for today. Just out of curiosity, I would just to have a feel of the audience. Who here worked with machine learning / data science? Okay. TensorFlow? Okay. Machine learning in general. Okay. Natural language processing. Python. Good. Okay, so we have a good mix. So some of the concepts of people who are experts may be too basic for you, but I will introduce them for the sake of others who didn't get in touch with them. So the plan for today is short introduction to natural language processing concepts. I won't be processing natural language yet. And then I will go with 2 demos with 2 examples. I will show you how to build a model in TensorFlow for sentiment analysis and how to generate the text, how to teach the model, train the model to generate the text. This will also be performed with TensorFlow, but using Keras, which is now #1 citizen in TensorFlow. And then a short introduction to how you can use Google Cloud to scale the machine learning process. And hopefully you will understand why you have to scale it when I show you those 2 examples. So when we think of natural language processing, there are plenty of tasks that you can think of it. Not all of them require machine learning. Not all of them require deep learning. Not all of them require TensorFlow. So when you think of part of speech tagging, it can be easily performed. Well, easily is a relative term. by some hard-coded rules. You can have a map of words, and part of speech could be the value in some kind of a key value storage, and you can perform tagging parts of speech in a sentence, right? You don't need machine learning for that. But there are some words that are ambiguous, like the word kind. Word kind can be an adverb, or you can use the word kind in a sentence. This is a kind of a problem, right? And it's not an adverb anymore. So if you have problems like this, then you think of something that is more smart. Maybe already you're thinking about AI/machine learning. But there are plenty of tasks, and some of them are very complex, and some of them are solved problems. For example, sentiment analysis is quite a solved problem, kind of. I will show you how easy you can achieve it. Two quite complex ones, like how do you generate the text that appear to be human? So let's start with more hard-code problems. When you think of a sentence, I walk down the street in a hat with a smile, and a problem of parts of speech tagging. As I said, you could use it, you could solve it with some hard-coded rules. But if you go with the sentence and try to build a system, a machine that will understand what this sentence means, that's a completely different task. And when you say that sentence to a person, to a human being, you probably have some kind of a picture in your mind, and you know that a hat is probably on the head of the person, but you don't have a specific information here. And a smile is not something you have, it's something that your mouth or your face is doing. So understanding is a completely different concept, something that we think is purely human. But let's think of sentiment analysis. So if you have a sentence, this film doesn't care about cleverness or any other intelligent humor, and again, we apply some rule-coded, hard-coded rules. For example, that would go and seek for how many words in that sentence were positive versus how many were negative. Let's say that's our algorithm. You would say this sentence sentiment is positive. But we know it isn't, right? This is actually a very bad review, well, a bad review. And a human being can obviously see it. A machine with the simple algorithm I just described would have difficulties. And again, you're thinking, maybe there should be something smart. Maybe we should apply some AI to solve this problem. And don't get me even started on subtle stuff like sarcasm. I don't recognize sarcasm very often when somebody tells me something. And it's not just about understanding the sentence like it was here, right? It's about understanding the context, understanding the person who is telling you that, understanding the relationship you had with this person. Much, much more complex thing. By the way, apparently, machines still cannot do it. So there's still some human stuff left for us, right? But when we think of natural language processing, I think we have, when I talk to people, we have this picture in mind. For those of you who haven't watched Blade Runner, this is the scene from Blade Runner, the old one, not the new one. And this is one of the pictures from the scene of replicant interrogation. So Blade Runners were supposed to recognize if this person is a human being or a replicant, which basically means machine. And of course, there were sets of questions, like how did you feel, what was your childhood, etc., that those machines could do. And this replicant, one of the main characters of the movie, asked if she can smoke, because this appeared more human. So this natural language, answering the questions, retrieving information is something that we pursue as human, but there are much more things that machines could do to mimic human behavior. So when we think of passing the Turing test, I think the sci-fi movies put us in these expectations. But the reality is that we're much more down to earth. We are using AI and machine learning, but to the text. So first, we work with text. Then we can make a robot around this, right? So I would say IBM Watson winning the Jeopardy contest, if you haven't heard about this, was like the first proof that AI is there, that there is a machine that can understand the question. Think of how many tasks it had to perform. Understand the question and understand which information it has to search for. Then it has to perform the search, find this information, and it has to actually answer the question in a proper way, so kind of like generate the answer. So a lot of tasks that are, we would think, purely human. And at the moment, we're not using machines to win Jeopardy. This was just a proof that there is a technology that works to do it. We use this technology for chatbots. Chatbots are, you know what chatbots are chats with the machine, with the robot on the other side. And there are a lot of tasks that chatbots has to do. Not all of the chatbots perform all of them, but like in essence, when you speak to the chatbot, you want to achieve a goal. You want to, I don't know, order pizza or buy flight tickets, right? And usually chatbots are not general purpose, so you can talk about the meaning of life. They are specified to perform specific tasks. For example, book you a flight ticket. So when you're starting a conversation, you're saying, I want to book a ticket from London to Porto, right? And the task of this chatbot is to retrieve this information. Book a flight from where? Oh, there is this missing information. When? When do you want this flight? So then the chatbot has to come back and ask for it. So once it asks for it, I'm saying, sometimes next week, show me the options. And the chatbot has to, again, retrieve this information and come back with the options. The actual booking, searching for flights, is not ML and not AI. This is something that, you know, our systems are already doing, systems that you probably built. The retrieving information, coming back with the answers is what ML can do. So retrieving information and generating the text. And I would say those are two main tasks that have subtasks or bugs for different kinds of things. And like chatbots and Q&As are the types of bigger tasks that contain some of them. Okay, so let us start with sentiment analysis. So I've shown you the picture, I've shown you the example how hard-coded rules won't just work. So how would you think, as human beings, how do we find out if something is good or bad review, let's say? Sorry? Feelings, yes, that's like very, very human thing. It's very hard to explain to the computer, you know, yeah, that's classifying. So it's very hard to explain to the computer, this is positive and this is negative, or this is neutral sentiment of this text, because there is such variety of text, right? But let's come back to classifying. I'm actually very glad you've mentioned that. So what's classification problem? For those of you who didn't work with machine learning, this is a classic machine learning problem. This is, if you take 101 course anywhere, you will learn about how to do a classification problem. And classification problem in terms of text would be to get examples of some text and classify it to some category. For example, we may take some articles, we may be a publisher, and we want to know if this text is about, this article is about politics, economy, maybe education, maybe art. And you can see already that this type of classifying can have categories that can like overlap. Maybe not categories, but like a text can be both about politics and economy, right? Or it can be about education and art. It can even be about economy and art, right? So depending how do you define your problem, you can have just one label, for example, or several ones. If we think of a sentiment, we can have positive, neutral, negative, or just positive and negative, depending how do we define our problem. Classification problem for text can also be, for example, if you have some monitoring or like ticketing system, let's say ticketing, and people can write some free text. And based on this text, you can decide to have an algorithm that assigns priority to it, saying like, this is urgent. There is a classic example that Google did with Ocado. Ocado is a grocery delivery company in the UK. And very often people send emails and they're just free text. Oh, I forgot to buy milk. Can you add it to my last order? And because there are so many customers, it's very hard for human beings to go through all those emails and prioritize. This is actually something that we have to answer right now. So they've built a system that is classifying those emails, and the urgent ones are prioritized and go to the person that has to take care of them right now, right? And the other ones, like they can contain feedback, it can be like some kind of like a bug on a page, they can be performed later. So those are different types, not exhaustive list, of course, of how can we apply classification to text processing. What I will show you at the moment will be reviews of the movies, IMDb movies. So this is called Large Movie Review Dataset. It's public, available for anyone, any of you to use. It contains movie reviews. It's already split into the training and test. So training is the data test that will be training the model, and test will be looking how this trained model, based on those examples, will perform on examples it has never seen. And it has two types of rating, positive and negative. And also it has like rating like stars from 0 to 10. So you can use either or both. I will just use positive, negative. There is a problem though. There is a challenge that free text is providing. If you have classical classification problem, you have features. Let's say you want to classify if there is a classical data set, census, and it classifies a person will be earning more or less than 50K per year. So you can have like a gender, you can have like education level, you can see like the area this person is living, the age of this person. So those could be features, and the label would be, will they earn more or less than 50K? In terms of text, well, every data point will be a document. Every label will be sentiment, was positive or negative, but what would be the features? And there are many approaches on how to make features from the text. Like, the first problem you could see is text can have different length and have many words. It can have sentences. It can be in paragraphs. So you have to find a way how to get this free text and fit it into this fixed length set of features. So how do you do it? I will show you one example, but there are much more of them. So let's have a look at this example. We have 3 documents. John likes to watch movies, Mary likes to watch movies too. First one, John also likes to watch football games, and third, both John and Mary like Titanic movie. So what I did was I gathered all the words from those documents, I sorted them, and this is my vocabulary. So at the moment, this became my set of features. So every word can be represented as one hot vector. So also has 1 and zeros, and has 1 in a second place and the rest is 0. So if you go back to this representation, it can be 1, 0, 0, 0, depending which word. How does it apply to the whole document, right? I will show you the encoder in a second, but let's think of how would we represent words. So this has 15 long vectors. Every word is represented by the 50 long vectors. But to be honest, this is not a corpus that we usually get. When we work with text, we have all sorts of words. How many words are in the English dictionary? A couple dozens of thousand, right? So the corpus is much, much bigger. You add names to it, you add slang to it, and it will become even bigger. So there is this technique that is called embeddings that is allowing you to make those vectors smaller, and this is called embeddings. So embedding is a technique or it's a set of algorithms that will give you numerical values to, first of all, change the dimension of those words. Sometimes it can get bigger. Like you can see embeddings that will actually make the vector space bigger, but it has the point. The point is it introduces relationships between words, relationships between vectors. What are the relationships between words? So there was this famous article, and it was showing the arithmetics that you could do with words. If you have proper embeddings, by the way, those are not real embeddings, it's just in 2D to show you how you can do the arithmetics. Usually embeddings have like 100, 200 length. So basically you could say a king is to a queen what man is to a woman. You can get this vector from here, applied to a king, and you should get the word that represents the queen. The same you could do with verbs, like walking is to walk, as swimming is to. Literally, if you get those vectors and do some arithmetic, I'm saying like adding and subtracting, you will get a specific words. And there are ready-to-use embeddings out there. You don't have to build them, but many neural networks are building them from scratch and making them integral parts of neural network itself. But there are a lot of resources out there for you to use, so you don't have to do it. You can just see what the research scientist has done for you. We will be using some encodings from Tensorflow Hub. Tensorflow Hub is a hub of TensorFlow models. Basically, you have there a database of pre-trained models, of models that have been trained at some point, and you can reuse, train more on your example, perform transfer learning, and it has text embeddings. So if you're working on some model, you probably can publish it there. It's all open source, of course. You can give feedback, and you can basically use the work other people did for you, so you don't implement everything from scratch. And in the example, we'll be using NLLM English Dimension 129 encoder. And what it does, it takes a sentence, or like a paragraph, and it turns it into 128 features. So basically, we'll get embeddings of the size of 128. And the beauty of it is, it's just one line. You just feed it with the sentence, and it will give you the embeddings. If you want to just search for it, if you want to see the insights, it's, as I said, open source, so you can see it. It splits the sentences on spaces. It uses embeddings for specific words, and then it uses those specific words embedding like in some kind of an average way to create embeddings for the whole sentence. The beauty of this is I have no idea how it works. All I care about is, does it work? Do I have a proof, does it work? The bad thing is I have no idea how it works, right? So if you ask me a question, I won't answer that. But because it's a community product, you can ask the questions directly to the authors, and they will know much better than I do. And because that's their job, because they are those community authors, they will have to answer you. So my neural network architecture, if we think of it, will be input layer of those embeddings, 128 input values from the sentence, 2 hidden layers, 512, 128, and the output. The output is just one cell because it will be either 0 or 1, basically. Sentiment is either positive or negative. And I will be using estimators, so I won't be building this whole neural network from scratch. I'll just say, build me a network with 2 hidden layers of those sizes, with 2 classes, and it will be classificator. Estimators are a very high abstract layer in TensorFlow. So if you ever look at TensorFlow like a year ago, half a year ago, probably some 101 tutorials will go as deep as matrix multiplication. You don't have to do it anymore. You can just use estimators. And they are just canned, and you can just describe what you want to achieve and don't go into details because they inside are optimized to work out those details. It's time for demo. So after I publish this demo, you will be able to run it for yourself. So it's on a platform called Katakoda. And if you go to Basia Fusinska, this is my username, you will find those. And you can see I'm not even logged in, so it's not like I have special access to it. You all can run it. So I will show you how we build and classify our text, the IMDb reviews. So first of all, I will run Python 3. I will just be using Python terminal. So I'm importing TensorFlow, NumPy, operating system Pandas, and TensorFlow Hub because I need this encoder I was telling you about. So it will take us a few seconds. I also wrote some functions in a help file that will load the data, so you don't have to do it. So so this is dataset URL. That's when you can just get the data from. This is how I called it. I will just load the data. So you can see it's a lot of data, but it should be pretty quick. Done. So it's now loading it, and we will now have a little look. How do they look? 50 seconds, 15 seconds. Done. Okay. And so the structure is we have a review as a free text, and we have a sentiment, either 0 or 1. I also shuffled it, so it will be different every time you're using those load data function. Test is exactly the same structure, just the test data won't be available during training. This is the text column. So basically what I'm doing here, I'm saying, take the column review, embed it using this encoder. That's the one-liner I told you that I could use from TensorFlow Hub. And then I'm building a classifier. So if you can see here, I'm saying, build me a classifier. It's deep neural network. DNN stands for deep neural network with 2 hidden units, one 512, 128. Use this feature column, this text column. I will have 2 classes and use this optimizer. If you don't specify optimizer, it has a default one, so it can even become, a little cleaner. Now I have to define an input function. Input function is a different way that TensorFlow is handling the input for either training or predicting things. It's a little bit difficult for people to like switch when you're thinking of training as this is my data, train on it. Here you're defining a function that knows how to retrieve the data. It's just a little bit of the paradigm switch. But the idea is the same. This function is just a function that knows how to serve the data. And now I'm training. So basically I take this classifier that I defined before, and I'm using train with this input function, and I'm using 1,000 steps. So you can see that the loss function is going, well, down and up, but that's normal. We just want, in the long term, the loss function to be minimized. And after 1,000 steps, we have a trained model. How do we know if our model is good? We can experiment and think like, if this loss function is below that point, we can stop. At this time, I just trained it for 1,000 steps. So let's have a look on how does it perform. I'm defining here a function that I will use as an input function for evaluation of my model. So just to have a look here, I'm just saying, you know, classifier, evaluate yourself using this input function based on the test, based on the trained data, and do the same with the test data, and then print the accuracy. So you can see I just used a canned estimator. I didn't tune my neural network. It's basically not even a type of neural network that you should be using for text, but it has quite a nice first try accuracy. With the training set, it has 80%. With the test set, it has 79%. Which, if you're like thinking of industry standard, it's horrible, of course. But this is the first attempt. Then you can tune it. Then you can think of some kind of a dropout. You can think of other stuff that you could do for this neural network. But very easily, with few lines of code, we have a trained system. And it didn't even take that much. I'll show the next type, and it will take much, much longer. Normally, it takes hours to train a model. So now we can use it to basically predict some examples for our purposes. So I created a function to do it. And the array of my reviews, this was an alpha movie, and I think it was great. You can experiment with yours. And let's see. I'm using a predict function here. This was an awful movie, sentiment negative. I think it was great, sentiment positive. Because it's 80% roughly correct, you will find some reviews that you could put there that won't be accurate. But I think that's pretty cool because this is maybe like 20 lines of code. It looks bigger because we have this narrow tutorial thing, but it's like really not a lot of lines of code. And we have our first classifier. So coming back to the presentation, let us have a look on how we can do text generation. And text generation is a big challenge in terms of, well, I would say using machine learning for real. Because, okay, you can create something that is generating text, but how would you use it? You probably want this text generated in some context. For example, when you have a chatbot, you want this to become natural, but also to provide the user with a proper information back, right? So it's not just about free text and feeling like a human being. It's also to like make sense of it, make it usable, valuable for your business. But what we are going to do won't be. We'll be generating a Shakespeare. So this is like a beginning of a corpus that you could download. So first citizen, before we proceed any further, hear me speak. So this is like a big text of Shakespeare from Romeo and Juliet, I'm guessing, but I'm not sure. Not an expert on Shakespeare. And our goal is to feed an algorithm with this corpus and say, now you go, generate me some Shakespeare. I don't know what's the practical usage of generating Shakespeare, but it is pretty cool, right? So there are plenty of challenges in that. Like for this poor algorithm that has to learn. First, it has to learn English, right? It has to learn how to produce words in English based on the corpus. Then, like that words have spaces, and so maybe it has to learn first words and spaces and punctuation and then English, right? And then it has to learn this play format, that there are people that are dialogues, like a person is saying, then is a colon, and then there is a line. And at the end, it has to actually mimic Shakespeare, right? Many people write plays. It has to learn how to mimic Shakespeare. So it has a lot of things to learn. So don't expect this poor algorithm to learn as quickly as the sentiment analyzer, right? Sentiment classifier. And this is actually a task that is taking context into account. When you think of this sentiment analysis, or if you are thinking of different words and sentences, if you think of them just separately, you don't have this context. But when you think of text generating, you have to learn from examples, start the text, and then think what fits after this. So this is a task when this context is very important. The algorithm has to have a concept of memory. And down to earth, with maths, with neural networks, it goes into predicting the next word, or even predicting the next character, which we'll be using here. And this is how recurrent neural networks were invented. Again, you don't have to understand fully the details, but the idea is that the part of the network is fed not only the input, like it was with deep neural network, but the information from previous steps. So if you have a sentence, you could think that the algorithm that is predicting next word from the word that you're feeding it also have information about the past, right? So this is mathematically, engineeringly introducing how you handle context. And this is what the type of input we'll be working with. So the algorithm will be predicting the next character. And characters are represented as integers. So we have 60 something, maybe 100 if you think of characters, depending which encoding we are using. So the dimension is not very big, but we'll be using embeddings to actually increase it. So the input data will look like this. We'll have some text of some length, first citizen, etc. So this is the first sentence, and we cut it here. And the target data, the label, will be something starting after we cut off the first character, but we add a character after. So this will be an input. This will be the target, the label. And I already did that for you. You won't be needing to do it, but it's a huge laborious work for any natural language processing task to actually prepare text in a form that is bearable by the neural network. So the architecture will look like this. We'll have those input characters fed into this memory, then embedding layer, then LSTM, which is long short-term memory, a type of recurrent neural network. Then we'll have dense neural network that will predict the character after this one. And we have this context idea here. This prediction will also be fed here. So the next prediction will get this character, the previous prediction, and it will predict another character based on the context and the input. And how do we generate the text? We're using multinomial distribution statistics. Basically, what comes statistically most probable character after the one that was fed, plus the context. I will be showing you how to do it with Keras, which is another even more abstract layer over TensorFlow, but it's a little bit confusing because I will be using it from TensorFlow, Don't think of it that much, just go with it. If you use Keras from Keras, it will work as fine. I'm using it from TensorFlow. It just does this up and down loop, but it works equally well. So let me show you a demo. So I'll go to here. So let's do text generation. And again, I'm running Python. I'm importing TensorFlow. I'm importing some other libraries and help functions that I wrote to download the dataset and to prepare this input and output all those characters. So let me set up some variables, read all of the things. This time it was much quicker, and let us print some things. So you can see this example of first citizen. It's a little bit shorter, but you can see that the F is cut off, and we have a character from the next word in that example. And if you go through those input and target values, you can see other ones. I will now reshuffle my batch, and let's start building our model. So I'm saying I'm having 512 units, 128 embeddings, and let us build the model. So it may not be as visible, but let's go through it. Like if I go to the presentation where the architecture is, we're expecting embeddings, LSTM, and dense, right? This is exactly what you can do in Keras. We're saying get the sequence of embedding, LSTM, dense. All you have to do is set up the dimensions of embeddings, how many units of LSTM, and what's the output of dense. Output of dense is predicted character, so it has the same dimension as how many characters we have, since I've put the vocabulary size, which is just how many characters we have in our vocabulary. Okay, we have this function that will build us the model. Let us build the model, and let's have a look. So Keras has this nice thing that you can see. Oh, actually, yes, I've built what I wanted to build. Those are all the numbers, all the layers I wanted, but it's not trained anymore. Now we just have to train it. So we're compiling it, saying this is the method that you'll be using to optimize, to train the model. We'll be using 3 epochs, so it will go through the training data 3 times. I will set up the checkpoints, so I will save the model to be used later, and let us train the model. So training the model is basically model fit. I'm saying which data set, how many epochs, how many steps, and this is just for saving the model, this checkpoint callback. So you can see ETA is 7 minutes, right? And it's just because I put small numbers. Normally, it requires much more time. Normally, it requires 30 epochs to give you anything of value. Like, I will show you the examples that I got after like first iteration. We may have time to go back and see, but probably not. So it didn't learn anything yet. So Romeo is the text that I put as an input text. So like you have Romeo and column, go. It didn't learn anything after 1 epoch, right? Well, like at least learn some spaces, right? No, after 1, no. After some time, it learned something. So actually, we'll go, like it even learned a dialogue thing, but you can still see, like it has problem with English yet, still, right? You can see all those words that don't fit. After optimizing, I used a little bit different LSTM RNN layer. It became pretty good. I mean, I'm not an expert on Shakespeare, but probably if I see something like this, I would say, yeah, it looks like some, you know, Queen Elizabeth time of a play, right? And again, like, if you go back to the demo, still learning, and it takes quite a lot of time. And even if you go through 30 epochs with this basic thing, you probably won't learn that much. You need a lot of tuning. You need some kind of a dropout. You need maybe another LSTM layer to actually get something specific. And this brings me to the next point, actually, because it's good to show sentiment analysis with small neural networks that can learn in minutes, because even this one is small and can learn in minutes. Usually, those algorithms take hours, right? If not days, if not weeks, if you want to get something that you can actually use in production. Yeah, to write a talk, that's fine, right? Even to write an article. But if you really want your company to get value from machine learning, from deep learning, from TensorFlow, building it is much easier now. And there are plenty of tutorials, plenty of talks, plenty of courses, even available for free. We have open source technology. But there is this stopping point at some, like, how do I accelerate my learning? So one of the ways is, for example, to accelerate it by hardware, right? Research facilities by GPUs. Thank you, gamers, right? We have GPUs for machine learning now because of you guys. I'm actually thankful because I'm not a gamer. So if you are, great. We have at Google Cloud a product called Cloud Machine Learning Engine. As a basics, it provides you a serverless way of running Python. So it doesn't have to be TensorFlow. It can be anything in Python. But you don't have to think of spinning up a virtual machine, anything like this. And you can attach hardware, like GPUs. I'm not sure about which stage TPUs are at the moment. I don't think they are GAs yet, but maybe they are, because it's changing so much. Have you ever heard of TPUs? Those are tensor processing units. That's a hardware developed by Google that is even better than GPUs, much better. Like we're talking 10x. But Cloud Machine Learning Engine allows you to attach this hardware, and you don't even have to think of a hardware in terms of computation itself, just saying I want to use GPUs, I want to use TPUs. For TensorFlow, it allows you to parallelize your training. So TensorFlow has, especially if you're using Estimator, has a way of using parallelized training and parameter servers. So basically the weights that neural networks have can be stored in parameter servers. The workflow can be distributed. You can say, I want 2 masters and 20 workers in a configuration file, run my workflow, and we'll just do it. And you don't have to think, how do they connect? How will it work? All you have to do is specify it in a configuration file. What's your parallelized algorithm requirements? On top of that, it allows you to do hyperparameter tuning. For those of you who don't know, there are plenty of hyperparameters in machine learning process. For example, with our dense layer, how many cells are in each layer? How many layers do we have? What is the learning rate? What is the dropout probability? And usually classically how things are done, data scientists are building this matrix of all possible values and try it one by one. And it's laborious, and of course, you can automate it, you can write scripts, but every researcher is doing it from scratch on their own. Maybe they have some libraries. Here, you don't have to do it. You, again, specify it in a configuration file. I want those hyperparameters to be tuned. I want you to try all those values, and it will just do it for you, based also on a metric that is your success metric. What it can do is also serve your model. Once you train it, you can serve it. So serving the model from pure TensorFlow is maybe not the most exciting task in the whole world. Here, once you have the model, it's being stored somewhere. You go to Cloud Machine Learning Engine and say, I want to serve this model. And it will just do it. It will create an API, REST API, that you can use in your application. And it has two modes. It can either be an online training, so it's an instant API REST call, or if you want to wait for the warm-up, you can perform a batch predictions. So you provide it with one API call with the batch, and it will give you the predictions. Your code, though, has to be a little bit rewritten, but just a little bit. It's just about the structure. So it has to have this structure. You have a project, and then you have this folder that is called trainer or somehow, but it indicates that it has to be this folder. And you have to do this init.py file. Even if you don't have anything there, it has to be there. It's required. And this is where your model is being trained. But you can have also other things, like your model actually can be defined here, and your task can use this model to train. But the task can also use some kind of a parameter. So let's say, for example, you want to use a different folder, a different value, so you can use those arguments to be used in task. If you want to build your model, you have to do setup.py. But if you're just using Google Cloud tools, you don't have to do the setup.py. It will be built for you. So once you run a command saying, submit my job, you have a job name, you have two modes. You can either say, this is the tire I want to use, and this is my package path, so basically trainer. This is my module name. Oh, sorry. Task. And this is where my job output, monitoring, etc. will be stored. This is the region. And those are arguments that are specific to this file task.py. Or the second way is you cross this out and you put your configuration in your config file. In your config file, you can also define the parallelized model that you want, if it's custom, and your hyperparameter tuning, but the rest stays the same. So it's just one command to run it into the cloud, and you don't have to think of spinning up any VMs. It's all serverless. So that's all. We went through natural language processing, I would say 102 kind of a presentation. We spoke about different challenges in the natural language processing task, and two different challenges: classification with sentiment analysis and text generation for Shakespeare. As I said, you will soon be able to do it on your own. And then I told you a little bit about how you can scale your workflow. And that's all, folks. If you want to talk to me, just stay in touch. As I said, I own all the domains, and I'm the only person in the whole world named like me. Either it's Barbara or Basia. So stay in touch. Thank you very much.